Welcome back to Applied Mathematics. In this video, I want to talk about significant digit analysis. There's a whole bunch of vocabulary that gets thrown around in this area of study that all comes down to the same thing. You may see it referred to as accuracy and precision. You might see tolerance, error, least count, and a couple of other ideas. But the issues remain the same. For a particular measurement, how far off of that measurement can you be and still be considered the same measurement? The answer varies drastically from application to application. Right? High precision machining very often requires the nearest thousandth of an inch, the nearest tenth of a thousandth of an inch, or in metric, in the micrometers or tens of micrometers range. In um, carpentry, a 16th of an inch is often more than enough. An eighth of an inch is perfectly acceptable in a lot of applications. And in between, everything in between exists. So there are a number of different conventions that come into these sorts of ideas. The one that I'm going to show you is the one called significant digit analysis, and it's relatively straightforward. The terminology of accuracy and precision is often used to talk about significant figure analysis, but I'm not too worried about the vocabulary here. The general idea is that accuracy refers to the number of significant digits in a measurement, and precision refers to the place value of the last significant digit. The obvious question from here is, what makes a digit significant? The answer is that every non-zero digit is significant, and some zeros are significant. Let's look at a couple of examples to try to make sense of those statements. A very classic example of why this sort of reasoning is important comes from early studies of Mount Everest. The tallest peak in Mount Everest is 29,000 feet above sea level. In the mid-1800s, a British survey was trying to measure Mount Everest and other geographic features near there and came up with this value. But they were concerned at reporting this because when you see the number 29,000 feet, Most people immediately assume that a measurement of 29,000 feet is a measurement rounded to the nearest 1,000 feet. That's not actually what the survey came up with. The survey came up with 29,000 feet to the nearest foot. And so, in order to make the number look like it was measured to the nearest foot instead of to the nearest thousands of feet, the measurement reported was 29,002. Right? It's taller than the measurement that was actually taken by the surveying team, but it looks like a measurement to the nearest foot. And so it's the first time someone put 2 feet on top of Mount Everest. More to the point, these kinds of ideas are what we are trying to think about. If we want to report a number measured to the nearest thousand of feet, then we have a relatively easy time of doing the measurement. If we want to report something as being measured to the nearest foot, we have to be more careful. So, in our significant digit analysis, we are going to report that these zeros are not significant. That is to say, we are going to assume that the zeros at the end of this value are part of a rounding and not actually measured precisely. Our equipment measured the height of Mount Everest to thousands of feet, to the nearest 1,000 foot, and that is to say that 29,000 is taken to mean somewhere above 28,000 and below 30,000, right? Putting a decimal point in, putting lots of zeros in to try to emphasize to exact value 28,000 feet and to exact value 30,000 feet. When we write 29,000 feet, we're assuming that the approximation is somewhere in that range. That's the quality of measuring equipment that we used to take this measurement. If we measure 29,002 feet, in this case, the zeros here are significant. We say that they are significant because they are sandwiched between non-zero values on both sides. This measurement is somewhere between, or somewhere above, 29,001.00, lots of zeros, and below 29,003.00, lots of zeros. All right, so that is the significant digits convention. The tolerance in our measurement is based on where it appears that we rounded the value. And so, when we talk about the measurement of 29,000, the precision there was the nearest thousand of feet, and it has two significant digits. When we talk about the measurement 29,002, that has 5 significant digits, and is precise to the nearest 1 or the nearest whole. If we switch from very large measurements to very small measurements, things get a little bit messy in different ways. So if we are measuring the width of a length of wire, we're measuring the diameter of the wire. Perhaps that wire is 0.037 inches in diameter. The zeros that come in the front of this number are forced to be there, right? Those are there to demonstrate the place value. So again, they are not significant. This measurement has 2 significant digits, and is precise to the nearest, what is that? 0.001, nearest 1,000th of an inch. And maybe that's what we have. But maybe we are using an incredibly precise measuring tool. And we did not measure this to the nearest 1,000th of an inch, but to the nearest 100,000th of an inch. 0.03700. These two zeros, we had no reason to put them into our report, right? Writing down the number, as far as a mathematician is concerned, 0.037 and 0.03700 are the exact same value. But as a measurement, they are not. As a measurement, the significant digits convention tells us that when we put those zeros in at the end of the number that we did not need to, they must mean something. We are going to say that they mean that they are significant zeros. We are saying that we measured this much more precisely and we got exact zeros at the end of the measurement, either because of coincidence or because of very careful machining. So this has those 2 zeros as significant, along with the 2 non-zero values. All told, that is 4 significant digits. Right. Instead of writing out the words significant digits, I very often see it abbreviated as sig figs. And it is precise in this case to the nearest 0.00001. Tenths, hundredths, thousandths, 10,000ths, 100,000ths. All right. So again, if I write the number 0.037, that means somewhere between 0.036 to 0.038. When I write the number 0.03700, that means that my precision is somewhere between 0.03699 to 0.03701. Right? This is not an applied sciences course. We're not going to use measuring tools in this course. So determining how much accuracy and precision your measuring tools have is a little bit beyond the scope of this course. But thinking about that and acknowledging that different measuring tools have different levels of precision is something that's important. Right? The difference between using a tape measure and using calipers and using a micrometer give you very different amounts of precision in your measurements. Different kinds of tools that can be used to perform operations give you different kinds of tolerances in how carefully you can perform operations. And a balance is made between how fast something needs to be done, how carefully something needs to be done, and how much it can cost to get the tools to make the thing in the first place. All of those are beyond the scope of this course. We're looking at what happens now. You have a piece that you have machined carefully to the nearest 10,000th of an inch. If you want to do calculations, how accurate are those calculations, right? You've machined out a cavity where you've measured the length, the width, and the height to the nearest 10,000th of an inch. How much precision do you have in the volume? Or maybe going the other way. You need to create a part that has a particular mass measured to the nearest hundredth of a milligram. How precise do you need to be in all of the steps that you take so that the mass comes out within the tolerance that you have? Those are the kinds of questions that we're going to be looking at moving forward. For right now, I have one last thing that I want to mention, and that comes back to that first example. When you have decimal values, figuring out accuracy and precision and figuring out how to report higher precision is easy. When you have large values, it's a little bit more challenging. So if I have 29,000 feet and I want that measurement to be reported as being accurate and precise to the nearest foot, a tool I can use is putting a bar, referred to as a macron, on top of that zero. It doesn't come up all that much because usually when these sorts of things come up, it's easier to go to scientific notation. But I could report that 29,000 as to the nearest foot, or if I put that macron here, it would be to the nearest tens of feet. And the last one, specifically when you have the nearest whole number, you can put a decimal at the end. That's the same as saying it is to the nearest foot. All right, so when you do not have a decimal point, zeros at the end of the number are not significant. Zeros in the middle of the number are significant. When you do have a decimal point, zeros at the beginning of the number are not significant. Zeros anywhere else in the number are significant. And when you need something other than that, you can put in a macron to make it work out. All right, that's all I have for you in this video. Next time, we will start looking at performing calculations and using these significant digit ideas to inform how to round calculated values. I'll see you then.